So today I want to go back and forth between some examples of diagnostics for deep convective precipitation and the way it interacts with its thermodynamic environment, moisture and temperature, analyzing observations and models on the one hand, and then using stochastic models, fairly simple ones, to understand why we see what we see. Asking questions like for the probability distribution of precipitation, does that have a physical origin, the characteristic shape of that probability distribution? I want to acknowledge graduate student Yihan Kuo, postdoc, now project scientist Fayez Ahmed, and postdoc Christian Martinez Villalobos in this work. Okay, so a couple of the things that we want to get to after a little byplay. In the upper left are probability density functions on a log-log plot of the accumulations of precipitation for events and for the daily average precipitation, where you're looking at the relationships between these. They have a characteristic form with the power law range followed by a more steeply dropping, approximately exponential cutoff. Can we ask questions about why this distribution has this form? Similarly, if you look at spatial clusters of precipitation, you see a qualitatively similar form. Can we get explanations for this and why this cutoff that separates these two ranges happens where it does, physically speaking? And then when we move to probability distributions of the column water vapor itself, they have characteristic shapes between, say, an ascent regime where you have low-level convergence and a descent regime. Can we give you reasons for why you have those shapes? What's the fundamental underlying dynamics? So I'm going to look at first observations and then model statistics in a particular form here. These are a set of 4 panels that are all related to each other. And I'm going to be showing you models in comparison to these observations. So let me take a moment to explain what you're seeing. On the leftmost panel, you have a conditionally average precipitation as a function of a measure of water vapor, although it's a particular measure that I will have to elaborate on. The different colors are different bulk temperatures. They're a tropospheric temperature measure. And the different curves have the precipitation, the conditionally average precipitation, increasing rapidly at a particular value for each temperature. A value characterizing the sharp increase has been subtracted so that these curves collapse with one another for each of the temperatures. And this dependence is not simply saturation, it's something more complicated I'll get to in a second. If you do a measure of the probability of precipitation exceeding some modest threshold, you get a similar rapid increase in collapse. And then if you look at how the thermodynamic environment itself is in this measure for precipitating points, you tend to have them clustered around the value where you had that rapid onset. And if you look at the column water vapor relative to its critical value, it does, out in the non-precipitating regime here, various things that will be governed by other dynamics. And when you get up to the region where you have strong precipitation onsetting, you tend to do the same thing over and over again, where you have this steep drop. Essentially, if you go into this regime, you are raining very hard and dissipating buoyancy. And so you have a drop in the probability of remaining up in that regime, but it has a finite scale over which you tend to hover in that regime. Now, it is worth taking a moment to put perspective on this before coming back to the same diagram. So if we think of our convective system here, the inputs are a profile of temperature and moisture, and the output we can think of as precipitation here. We're splitting the overall problem into 2 parts. One is what sets the threshold where you get the rapid onset of precipitation. In the tropics, this is primarily conditional instability, and that's what I'll focus on today. So you get a buoyant, deep convective plume when your water vapor and temperature reach a certain configuration with respect to each other. And the details of this matter a great deal for the quantitative simulation in your climate models, as I'll show in a moment. And then most of the talk, the stochastic part, will be, given this threshold type behavior and this rapid increase, can you explain a number of important features about the probability distributions of precipitation? So I'm just going to show you one slide background, a brief word on the threshold itself. So you're going to have some buoyancy of a deep convective plume depending on these inputs, moisture and temperature. Empirically, there's evidence that air is being entrained, whether dynamically in coherent flow, the way the mesoscale community likes to draw it, or in turbulent flow, the way conventional cumulus modeling tends to think of it, or more likely some combination of the two. In any case, you entrain air through the whole lower troposphere in a manner that gives relatively equally weighting to layers through the bottom 4 kilometers. Of course, if you're bringing in dry air, you tend to have a negative impact on your convection. And between those various factors, of course, if you're too warm, you also have a negative impact, although you're increasing the amount of water vapor your air can hold. Between them all, the integrated column water vapor, which we have a lot of observations of from satellite, ends up being a sufficient measure of the lower tropospheric water vapor here that relative to its temperature dependent onset becomes a crude measure of buoyancy. And in work that I can't talk about today, you can refine these measures of buoyancy using different layers, and that's a subject of a talk all by itself. And then I should also mention that these everything I'm saying here holds for relationships at fast time scales. You're looking at instantaneous to hourly type data in all of this talk. And because the long-term time average obeys different balances involving different large-scale balances of the energy and moisture equations. Okay. So back to the exact same slide that I was showing earlier. And what we've added by this little sidestep is that we are interpreting this column water vapor relative to the temperature-dependent value where it onsets as an empirical estimate of buoyancy. And so in the stochastic model, we can run a column water vapor equation and use the fact that we have this rapid onset of precipitation as an empirical input establishing what happens when you hit the precipitating regime. Okay, so these are the observations for the onset and precipitation, how long you spend in the non-precipitating versus the precipitating regime, and what part of that is for precipitating points. Let's look at some models to see how well they reproduce this. So here, for example, is the GFDL model, same format of diagram. This is for one particular convective parameterization, and it's doing pretty well. The onset is well represented in conditional average and in probability of precipitation. Your precipitating points are fairly well confined near this onset. You have some interesting behavior as you move. Remember, these different colors are different bulk temperatures of the troposphere. As you move to the warmest temperatures, you're getting some odd things, including this extra bump at very high water vapor going on the model that we did not see in the observations. And then you have this spread out in the non-precipitating regime that will be something to explain later. If we switch convective schemes in the same model to the Donner scheme, you get qualitatively similar features, but the details change quite a bit. Your onset is now a function of temperature, and you have a very broad distribution here, still this sort of double peak effect at the very warmest temperatures. And just surveying a couple more models, here's the Canadian model, in particular version. It has some version of the pickup, but it's a little bit anemic, and it sort of has a two-stage effect. Pointing to questions about the convective parameterization and the large-scale parameterization. and very broad precipitating PDFs. If we look at EC Earth, it's doing basically great. The pickup perhaps doesn't extend as high as in observations, but everything is more or less in the right place. If we look at CAM 5.3, it's also doing quite well. You have this tendency to different behavior, this little extra bump at very high temperatures. And I should point out that if you're going to use these models for global warming, the fact that you're doing things a little oddly in the high temperature, high water vapor regime is something that would be of concern. We can just briefly check what if you switch to a super parameterized version of this same NCAR model. In other words, you're running a cloud resolving model under every grid cell of the climate model. And again, you've got qualitatively the correct behavior, the pickup, but you tend to have rather broad PDFs of the precipitating points. So it was not a magic bullet in and of itself to use the super parameterization. Okay, so summarizing that, just putting multiple models, the ones you've seen plus other ones. This is for the probability distribution of column water vapor shown here for something like a descent regime and an ascent regime. The models are doing generally the same thing, peak at low water vapor here, dropping off, ascent regime packed up towards the place where the onset would happen, but with a fair amount of variability in exactly what goes on there. So you'd like to have process models, in this case stochastic models, to help identify what is the physics underlying this, both in observations and the type of sensitivity that you might get in these full models. One more thing in this same format, which is showing the statistics you just saw, but broken out by mean ascent or descent regime using monthly average 500 millibar vertical velocity from the ERA interim reanalysis. This is in observations. The pickup in the conditional average precipitation, probability of precipitation is going on same as before. This is shown for one particular temperature, and the different colors are now the ascent versus the descent regime. And the big difference that you can see is that there's now a very sensible behavior in the descent regime with low-level moisture divergence. You're tending to peak at low water vapor. You spend a long time in the non-precipitating regime. Then you have this slow drop, this is a log plot, out to where you have a much more rapid drop when you get to the onset of precipitation. Whereas if you're in this, the ascent regime, low-level moisture convergence, you tend to be more commonly confined towards the onset of precipitation. You spend less time in the dry regime out here. But once you're in the precipitating regime, you tend to have a drop in a similar way in each case, with the large-scale dynamics being less important. Okay, so the stochastic model to explain this behavior, plus some other things involving the clusters and the probability distribution of precipitation itself. At the top is a moisture equation. You have the time derivative of moisture, and then you have a moisture convergence term here. This MQ is, it's a vertically integrated moisture. Our Q is the column water vapor, and MQ is proportional to moisture, but it's containing a factor that involves the vertical structure of the wind and the moisture relative to each other. If it was just a layer model, this would just be the moisture itself. You're evaporating and then you're precipitating, and the precipitation is a function of moisture that captures that empirical sharp increase. Here we're just using a ramp function in most cases that I'll show. You can, so you've got this moisture budget, you can run this in a 2D domain, or you can look at a single column at a time, and I'll show you examples of both. What do you do about the divergence? The simplest case is you specify it as a climatological divergence plus an autocorrelated noise. Note that it'll be a multiplicative noise because this is essentially proportional to moisture until you saturate. You can, for simplicity, also switch this model out with one where you replace this whole moisture convergence term with just a mean moisture convergence plus a specified noise. That will give you some results that are relatively similar for understanding, for instance, PDFs of precipitation. Now, there's going to be an important feedback when you're rating from the temperature equation or dry static energy equation, vertically integrated as we're using here more specifically. Your divergence is going to be balanced. The adiabatic cooling is going to be balanced by the latent heating, which is proportional to the precipitation in the vertical integral. And so you're going to get a feedback. You're going to have a net flux into the column tending to force this. You're going to have a noise term from all the gravity waves and so on, changing your d by dt term that has been, as well as v dot grad t and any random fluctuations in the flux wrapped into this sort of divergence driving term. So your divergence will have a feedback with the precipitation, and if you check about substituting this back into this equation, you'll see that precipitation arises twice, and it's going to end up multiplied by a term, there's a parenthesis slightly wrong here, but a term which involves the moisture stratification term relative to the dry stratification term ms. So that'll be a relative gross moistability, measuring the amount of net energy you get when you cancel the diabatic heating and the adiabatic cooling for a large scale uplift. Okay, so that's our simple thermodynamic stochastic model that we can use to try and explain some of these features. Now let me remind you, I'm just going to zoom in on one panel of the thing that you saw last time. This is the PDF of moisture when you're dividing by ascent regime and descent regime. In the descent regime and observations, you spend a long time at relatively low water vapor, but you slowly drop until you hit, in probability, until you still sometimes hit the precipitating regime. And then if you're in an ascent regime, you spend more time up there. Can we explain the shapes of these distributions from that stochastic model? So here's what you get. These are actually analytic solutions from a version of that stochastic model you just saw, including the multiplicative noise. You're forming the Fokker-Planck equation for the stationary distribution, solving that analytically. And the elements that you get in the non-precipitating regime include a typical scale with a 1/q that's giving you your rapid rise from low moisture that you see here. And that scale involves the evaporation relative to the amplitude of the noise. And then you get this long power law regime whose exponent depends on the divergence. So in the descent regime, even though you have a peak at low water vapor, your noise will sometimes manage to get you up to quite high water vapors where your precipitation onsets, and then you enter a new regime. The precipitating solution is somewhat more complicated, has generally the same form, but the coefficients get modified by the fast time scale of the precipitation in that empirical rapid onset. And so you get a rapid drop of the probability of precipitation with a characteristic scale that depends on that time scale in the precipitation. And that goes on approximately the same, whether you're in the ascent regime, the low-level convergent regime, or the low-level divergence regime here, or neutral in between. And then once in a while, you'll manage to hit large-scale saturation. Essentially, you'll have reached such high water vapor that you saturate your column, in which case we've parameterized that as a steeper drop down here, a faster time scale of conversion of water vapor. So that's using the moisture equation only with the specified divergence case. If we move to the one that also has an energy equation and includes the moisture feedback, we get a very similar form. It's just a little step more complicated than what we saw before, so I'm not giving you the whole expression. The descent regime is an exact analog, except it's forced directly by the flux into the column. And so you get, for the descent regime, spending a lot of time at low water vapor, but this long power law tail up to the onset of precipitation, and then this steeper drop. But the coefficients in here, the dependence in here, has a more complex form. A key term involves an integral of the precipitation as a function of moisture, which is the loss term. This gross moist stability, which has a 1 minus moisture relative to some dry stability term here. And that's reducing the effects of this loss by additional moisture convergence. And it's all relative to measures of what's happening in the variance of the noise. So there's greater sensitivity here. You can change this shape. In fact, if you have a region of negative gross moist stability, then this curvature can change and you can actually get a little bump before the saturation regime. So it's much easier, it can be much easier to reach the large scale saturation regime. So remember, in the models in current climate, we have these funny double bumps sometimes at high temperature. This is a different example of a PDF of water vapor relative to its critical value. It's a slightly different measure of the critical value. For two cases, one is a historical run and one is a representative concentration pathway 8.5 global warming run. You're showing two temperatures for each case, a lower temperature and a high temperature. And as we move from, say, for the higher temperature case, from the current climate to the future climate, everything stays more or less the same in the bulk of this distribution once it's moved relative to its critical value. But the longer than Gaussian range out here changes quite a bit. So you're spending more time in these extreme event ranges. Can we get an analog for that in the simple stochastic model? Well, yes. This is showing in red here a representation of the current climate, where you have a certain value for the critical water vapor for onset, and then another case at a warmer temperature representing the future climate, where your onset is at a higher value. There are two curves shown here, and they make slightly different assumptions for what happens to the dry stability as the climate warms relative to the change in the onset for convection. In one case, you continue to get a fairly steep drop in the probability of your extreme event, extreme water vapor events associated with very high precipitation. In the other case, you've begun to develop a bit of a double bump here, where you have slightly less adjustment of the dry static stability. And of course, if you push this behavior even farther, you can get a full double bump. So this is an analog for what's happening as a function of temperature in the models in current climate, and also for what is being represented in the models in a future climate. And it focuses you on the particular physics that's relevant to these changes in the probability distribution, the PDF, in the high temperature, high water vapor regime. And when you look at the precipitation distributions from such a model, they can scale at greater or less than the Clausius-Clapeyron, depending on what's going on in this region up here. So it depends on the gross moist stability. Okay, so speaking of that, let's move to understanding the probability distributions of precipitation itself. Let's begin with a idealized time series of precipitation with the time axis running along here. And in a single day, you could have multiple events where the precipitation starts, stops for a while, starts again, stops for a while, starts again. You can have very long events that continue for most of a day. They can even, of course, go over the boundaries of your day. You can have days that have no precipitation. But one of the points here is that if you look at one measure, which is the accumulation of precipitation from when your event started, integrate all the way through until when it stopped, that's actually going to be a simpler measure of precipitation amount in the following sense. It only depends on the dynamics of the precipitating regime. If you look at a daily average or a 12-hour average or a 5-day average, you're going to be mixing properties from the non-precipitating regime and from the precipitating regime. And so you're going to get a mix of dynamical regimes in that time averaged intensity. And so what we're going to argue here is that even in the time averages, some of the simplicity of the distribution of event accumulations, which we will also explain, gets inherited by the time averages. Okay, so on the left is the observed. I showed this in the intro in the second slide. Distributions on a log-log plot of the probability of getting different sizes of precipitation events. The blue line with the steep drop in the power law range here is the distribution of the accumulation, so rainfall integrated from when an event started to when it stopped. And that's dropping at a steeper than with a steeper than -1 exponent. In this case, it's about -1.4. These are for Department of Energy observations at Manus Island. You can do it at various places. When you average this up to a daily, you still have something that's approximately a power law range here. And when you look at this steep cutoff where you begin to drop roughly exponentially, that cutoff tends to match between the averaged intensity and the distribution of the accumulations. And then if you look in that stochastic model that I showed earlier, you can reproduce this behavior rather well. Now, one thing to be said is that the precipitation time average intensity has been approximated by a gamma distribution for decades, starting with Thorne 1951 was the earliest I could find. So as soon as this exponent is less than -1, you can use a gamma distribution, which will have the power law range and the cutoff. And what we're going to say is that that actually has physics to it, although in the time average, it's only an approximation. Okay, so to summarize, let's talk about the relationship between the daily average and the power law range. And I don't have time to go into the details of this, but simply summarizing the bottom line. Given that you have this accumulation distribution, and the accumulation distribution, its power law exponent tends to be the same across different meteorological regimes. When you move to a daily average, you're going to be in a given day often averaging several events. So the amount that falls in a day versus during an event will move probability from the small events to the large events. But you're going to essentially be having a weighted sum of variables pulled from this distribution. And you're going to end up with something that, if the time average does not introduce any scale in your distribution, will have to be still approximately a power law. And it is approximate, not an exact power law here. But you won't have a strong scale dependence here, and it'll be a less steep slope simply because you've added up events. Once you get to the power law less than -1, this is similar to saying that if you take samples from a gamma distribution and you add them together, you will get a variable from another gamma distribution with a less steep slope. Okay. So the cutoff scale then is getting inherited from the one in the accumulation distribution. So we'll give it some physics of that and some consequences of that, and that will get inherited right through all of the averages. Okay, so here's an example of looking at accumulations in a climate model. This is from 2017 study. The simplest theory, where you just say your precipitation has an on-off switch, gives you a very simple first passage process for which the exponent is -1.5. When you have the ramp function in the stochastic model, it comes down to around -1.3, which matches what you get from the full community Earth system model fairly well, shown for different regions here, in each case with a roughly exponential drop-off above a cutoff scale. That cutoff scale is given by the competition of the moisture convergence against the precipitation loss. So as you go to a future climate with higher moisture, you expect that scale to extend. But I should say that if there are dynamical effects, like a change in the amount of convergence that you get, that goes into that exact same scale. So you've got a very simple situation, just one thing changes. So if we do the experiment of running the climate model in the a greenhouse warming scenario, again, representative concentration pathway 8.5, end of century, you find that essentially the accumulation size scale rescales. You move your cutoff scale out a little bit so you drop less quickly. And this is on a log scale, so a factor of 10 is shown by this arrow here. So you're getting fairly large changes in the extreme events. And in fact, if you do a risk ratio, it goes up roughly exponentially and can reach 1,000% increase in the very largest event in the climate model projections. Does this occur in observations? Yes. This is looking at the US hourly data sets forming accumulations, and this is the risk ratio for accumulations for certain regions shown above, and then the daily precipitation intensity risk ratio shown below for 2 sort of decade-and-a-half periods in the a more recent period relative to an earlier period. And without attribution of this, you can say that when you do have this type of change, it follows the form that we have been arguing for with this approximately exponential increase in the risk ratio. Okay, so let's summarize graphically some of the dynamics that's going into this. First of all, for this probability distribution of precipitation, the power law range in the accumulations is coming simply from as you're moving, as your dynamics is changing your water vapor, you reach a threshold where you begin to precipitate, schematized by these filled in blue areas here in this time series of the water vapor. And you're going to tend to fluctuate back and forth across this threshold. If I illustrate this as a random walk with the time axis coming out here, moisture running up this way, your random walker is wandering back and forth across this threshold. Let's say this is up on a sidewalk and this is down in the ditch. The up on the sidewalk is the raining regime, the down in the ditch is the dry regime. The random walker will stagger back and forth across this. The PDF of the water vapor value relative to that threshold will tend to increase as time to the half if you're moving forward in the simplest possible case. So the flux across this will go like that time to the negative 1.5. And of course, it's not quite time, it's the accumulation of the accumulation of the rainfall that's your true measure of the passing time in each of these events. But anyway, that gives you this steep roughly 1 minus 1.5 range here in the simplest case. And then when you get to, and that's quite robust, it doesn't have any amplitude dependence on your parameters, and it tends to stay the same from regime to regime. When you're talking about the cutoff, if your precipitation that you've rained out during the event is growing with time, that will continue to grow. That's initially a slower growth because it's scaling in the simplest case like time if you had an even precipitation rate. And so it will come into play later in the event, so for the larger events, and will yield this cutoff that balances the precipitation loss against the moisture fluctuations. When you do a time average, you're simply taking a number of these events and adding them up together. You reduce the probability of a small amount in that averaging window increase the probability of a large event in this range here, but the cutoff has the same physics and is inherited from what we had in the accumulations. And then if you think back to the relationship to the thermodynamic environment here, what's going on in the precipitating regime is dominated by that precipitation physics and is thus relatively simple and relatively similar, whether you're in a large-scale ascent regime or a large-scale descent regime from a climatological point of view, whether you're being driven by positive net fluxes in the column or negative net fluxes into the column. But you will, when you exit the precipitating regime, you will obey different dynamics with the large-scale ascent. The descent regime will have a peak at low water vapor, although as we saw, it has this fairly slow drop until you hit the precipitating regime. So you still sometimes get precipitation even in a dry zone. And then in the convergence regime, low-level convergence regime, you're just returning yourself more expeditiously into the precipitating regime. When you're wandering around in the dry regime, you have a drift upwards towards the onset that returns you there. Okay, so now let me switch over just briefly for a few slides on the spatial clusters. So you have large spatial clusters. Their probability is dropping relatively quickly. Again, in a log-log plot of the probability of a measure of the cluster precipitation. This cluster power is just the precipitation integrated over a contiguous precipitation cluster. And when you look at the smaller clusters, they have a roughly power law range. Again, the exponent is around minus 1.5. So you are tempted to think that there must be an analogy of theory for the time-dependent case. You would suspect that the cutoff contains important physics and that it would be susceptible to change under global warming. If you look in a series of climate models, here the PDFs of the cluster power are being shown separated by 2 decades just so that you can see them. So we're shifting them up as we go along, but you can compare the slopes. In each case, you have a range which is roughly power law, roughly in the range of minus 1.5 exponent, followed by a roughly exponential drop. If you look at the blue is historical versus end of century is purple, you tend to have an extension of this cutoff and thus an increase in the probability of the various largest events. And indeed, that tends to have a roughly exponential increase in the risk ratio with the size of the events. So can we do this in the stochastic model? This is an example of a snapshot of precipitation from a 2-dimensional version of the stochastic model in the box. There's a slight large-scale convergence driven by fluxes in here and a slight descent out here, so it's like a very gentle Hadley cell, and there's stirring by a stochastic purely rotational flow, as well as the tickling of the divergence as we saw in the earlier equations, and then feedbacks of the divergence in the precipitation. Because we have a weak temperature gradient energy equation that gives that feedback as we saw before. So do we get the cluster power distributions? Yes, about a minus 1.5 long power law range followed by a cutoff. Here is just testing the sensitivity of the cutoff to thresholds of the precipitation. And then we're interested in what moist physics would govern this. So it turns out, yes, the cutoff depends on moist physics. You can do a series of parameter perturbation experiments with things like the amplitude of the noise, the evaporation, the critical value at which the precipitation increases, the diffusion, the time scale of the precipitation loss rate. And in each case, you find that the power law range stays about the same and the cutoff tends to change. And then you can furthermore do experiments mechanism denial experiments where, for instance, you have or don't have interactive radiation, that has a modest effect, where you switch the diffusion off, that has some effect, where you take out you do specified divergence instead of feedback, that has a large effect. And essentially, you have multiple aspects of the moist physics that is going into that cutoff scale. So it's of interest to see if you can make sense of that multiple dependence on the moist physics. You've established that the cutoff scale is important. It's the thing that changes. What's a very simple process that we could use to represent this? The stochastic branching process is a tempting analog, because if you start with one precipitating cluster, it can add neighbors in the next time step corresponding to a probability of generating branches in a stochastic branching process. And if you follow forward by units of time, you keep adding clusters, keep adding points to your cluster or losing them. That corresponds to a stochastic branching process tree moving forward in time. So if you grab an example that seems relevant, the mean number of branches per generation is the important parameter. And if these are Poisson distributed, then the probability distribution for your stochastic branching process would be the size to the -3/2, which is the correct exponent for our power law range, and then an exponential drop with a scale that is given in terms of that mean number of branches. So then you jump in, you diagnose for a given run of your model a measure of how many pixels you tend to add to your cluster per time step for a growing cluster. And then we want to check if that helps us any with the parameters sensitivity. Can we collapse that? So in the top case here, this is our parameter perturbation relative to a reference value. This is the percent change in the cluster area and the, excuse me, I go back one slide, cluster area and the cluster power, the integrated precipitation. So that's the raw input. If we instead display the x-axis as being this cutoff scale that we expect from the branching process, what we find is that to a reasonable extent, for both the area and the power, we collapse onto a single dependence for all the parameter perturbation. So what this says is that, yes, the cutoff scale is important. It depends on various aspects of the moist physics, but you can boil it down into what's the probability of generating new neighbors once you start convecting. Okay, and that brings me to my summary. Essentially, your stochastic model helps you with several things. It demystifies the power law range that you see in the probability distribution of precipitation, both accumulations and time average intensities. It establishes the relationship between those two probability distributions. It gives you moist physics associated with the roughly exponential cutoff of these distributions. And it tells you the relationship to the thermodynamic environment as you move around in water vapor, driven by complex dynamics, which we've here represented as stochastic. So at this point, we have reasonable theoretical underpinnings for the diagnostics of the models and of observations that we showed you at the start of the presentation. And I think I'll stop there, see if there's time for questions.
Yeah, thank you very much, David. We have a few minutes for questions from the audience. Michael, no, you should use a microphone, otherwise he won't understand.
Hi, David. Good to see you even from a distance. Thanks.
Hi, Michael. I can't quite see you, but I can recognize your voice.
Yeah. Well, these go well one way, but not the other. So, well, to the extent, I mean, this was pretty impressive, and thank you very much for taking the trouble. Any concrete advice to those poor GCMers about how they might improve their Precip parameterizations from collapsing all these distributions and finding branching models and stuff?
When you get to a particular GCM, you are needing to get down into the weeds of the parameterization. One substantial factor is the representation of entrainment, and that was the thing that I summarized in one slide. In order for this talk, I wanted to emphasize the stochastic modeling and the explanations arising from that. That one slide summary of what sets the onset is one of the things that you most need to take apart when you're looking at what a particular model is doing. You can, for instance, we've done examples with CESM of pulling out the piece of the convective parameterization that does the conditional instability computation for the plume and looking in detail at the dependence of that. And that's an example of the sort of, when you want to map this onto the specific details of the parameterization, what you need to do. But I think the stochastic model gives you all the pieces that you need to understand how these things relate to each other. And so, for instance, if you're worried about your high-end precipitation and its probability distribution not being strong enough, you know what factors are tending to impact that as you move through the pieces of physics that you're looking at in your code.
Good, great. Thank you very much, and hope to see you soon.
Okay, great. Thanks.
Thank you, Michael. Thank you, David. Any other question from the audience? Oops. Maybe.
Yeah. Hi, David. It's Roberto Buizza. I was at the European Center till 1 year ago.
I'm sorry, I'm having a little trouble hearing.
Okay, Roberto Buizza. Can you hear me? Can you hear me? Hello?
Yes, I can hear now, just.
Okay, so it's Roberto Buizza from the formerly European Center.
Hi.
Okay, so what I want to say is a comment on the actual resolution of these GCMs, and we shouldn't forget that with a resolution delta X, actually what the GCMs are able to resolve are, roughly speaking, 5 times the grid resolution. So if we're talking about models used for climate studies, the models are now have a resolution of about 50 to 100 kilometers, which means that they are capable to actually resolve scales only down to 200 kilometers or so. If we're talking about weather models, no, they are running now at about 2 to 10 kilometer resolution. Again, a factor of 5 will bring you to 10 to 50 kilometer actual resolution. What I mean actual resolution, I mean that the model spectra, energy spectra, is similar to the observation spectra. So when we are trying to judge the quality of the models in predicting Precip, we should really keep this in mind. The models are really trying to simulate precipitation over scales, which are still rather coarse. And often we compare model simulation to observations, sometimes average, but still observation captures a lot of very small details that the models that we're using now are really not capable to use. So it's very difficult to comment on the taste of the distributions. One can say much more about low value of precipitation, 10, 20 millimeters an hour or so, but it's very difficult to say something about values higher because the models are really not yet there. Despite all what we can do to the parameterizations, the scales are not resolved. And I don't think that stochastic processes can actually help us a lot because even with stochastic processes, the scales that the models are capable to resolve remain roughly what I said, which is about 5 times the grid spacing.
Yeah,
I don't have a question
those
there.
are
It's just a comment.
Those are all very good points. One, in comparing to observations, of course, one thing you can do is you can coarse grain the observations and check for each statistic you're interested in what is the dependence on the spatial scale. That's one thing that is worth, one necessarily does. But one remark from the results here is that for some aspects of the distributions, a very simple stochastic model is giving you explanations of the observed form of the distribution, including out to quite high precipitation intensities. And that means that there's something fundamentally simple about what's going on. Wherever we have simplicity, we should exploit that, because precipitation is, as you mentioned, a complex process. So knowing that there are some simple underlying considerations that are governing essentially all the percentiles of the distribution, except perhaps the very unusual event, is highly worthwhile. And in some sense, as you add resolution to the models, this would say you're essentially having an expensive noisemaker from the point of view of some of the features of the precipitation distribution.
Right. Thank you, David. We're a little bit pushed by the time, so I think we need to come to an end of this video presentation. I think we should all thank you again for having made it. It was it happened very well. We could hear you very clearly, and the slides were extremely clear. So thank you very much indeed.
Yes, thanks so much for having me.